And welcome back to yet another AP Chemistry FRQ answer video, and this time we're answering FRQ number 3 from the 2022 exam. And without further ado, let's go ahead and get started on the answers. If you want to access the PDF, there's a link in the description box down below, so make sure to check it out and follow along, or you can use the link shown in the video right now to put into your search bar. And just a quick reminder that this is not affiliated with the AP College Board in any way, shape, or form. This is just a video answering the FRQ questions. Alright, with everything out of the way, let's go ahead and get started with question 3A. And I'm sure all of you who took the test this year got super happy when you saw this question. I took this exact test this year, and I was so happy because this was an easy 1 point to get. You simply just use the periodic table and do electron configuration. So starting off with aluminum, it's going to be 1s2, 2s2, 2p6, 3s2, and finally 3p1 to reach aluminum. And that would be your final answer. Also, one thing I have to note is that for the first time this year, the College Board actually provided like a separate booklet with the AP reference sheet and the periodic table. So it was really nice having an easy reference to kind of flip back and look at. And I think in the past what they did was they had the periodic table and reference sheets like in the same booklet. So then you had to like flip the page back and forth, and that just made it so much harder because it wasn't right in front of you. And I think this year was the first year they actually changed that. So I'm really happy. So yeah, keep doing that. Anyway, for question 3B, we have this, and it says that we're given a claim that the aluminum atom is larger than the aluminum 3 plus ion. So what does an aluminum 3 plus ion actually mean? Well, to explain this, I'm going to use a periodic table, so I'm just going to pop one up. And so for aluminum is right here, of course. And then for aluminum 3 plus, it means that it's lost 3 electrons. So as it loses electrons, it's going to go from magnesium, which is 1 electron lost, then 2 electrons lost, which is going to be sodium, and then 3 electrons lost, which is eventually neon, and it's going to have the same electron configuration. So if you notice, aluminum actually has one more energy shell than neon, which we'll actually use that type of information later. So now let's go ahead and put down our claim, which is that aluminum is larger because of effective nuclear charge and Coulomb's law. How do we know all that? Well, for the effective nuclear charge part, my teacher always says that this is the power of the proton. And here's why. We know that aluminum has 13 electrons, but the aluminum has 13 electrons, but the aluminum 3 plus has only 10 because it lost 3 electrons. Because aluminum 3 plus has 3 less electrons than aluminum, there's a greater proton to electron ratio, and so there are more protons than electrons, so the protons can actually pull the electrons in more, causing a smaller molecule. Likewise, the aluminum atom is larger because since it has more electrons, the ratio to protons to electrons is much smaller, making the force pulling the protons and neutrons together weaker, and so the atom will actually be larger in comparison. Now, to justify using Coulomb's law, remember that the aluminum element has one more energy shell than aluminum 3 plus or neon, and because of this difference, the electrons in aluminum are farther away from the nucleus, which causes a weaker attraction and thus a larger molecule. And a quick tip when doing comparisons like this one is that AP College Board actually wants you to compare both elements. You don't want to say why aluminum is larger, but you also want to mention why aluminum 3 plus is smaller. So to give a reason why aluminum 3 plus is smaller, you can say that it's because it has one less energy level, so the electrons on the outside will be closer to the nucleus, which is full of protons, and it'll cause the force to attract them to be closer and a lot stronger, making the entire radius and ion smaller. And this next question, which is 3C, is a really interesting one because it doesn't involve any math or any equations to use. It's simply asking pretty much how well you paid attention during the lab part of chemistry. So we have a table, and for step 1, it already says that they used a weighing paper and determined the correct amount of the silver nitrate. We now have to fill out the next few steps in order to dissolve the solid to make a standard solution. So for the second step, you want to add in enough distilled water to completely dissolve the the silver nitrate. You don't want to add the solid and then all of the 200 milliliters of water because it won't dissolve well. You want to make sure that you add in just enough distilled water until the solid dissolves, then place that small solution into a 200 milliliter flask. You actually want to use the 200 milliliter flask for the measurement to be more accurate because using the 250 milliliter one is very accurate for measuring 250, but not for 200. All right, and then for step 3, we want to make sure that all of the solid was transferred correctly. So I'm going to say to use a pipette with distilled water and to rinse off any excess solid from the weighing paper that didn't get put into the beaker. And this will actually help make sure that all is added into the water. And then for step 4, you want to make sure to stir the solution with the solid to make sure, of course, that everything is thoroughly dissolved. And then for step 5 now, you want to fill it up to the 200 milliliter line. So using a pipette, place enough distilled water until the line hits the 200 milliliter mark. And remember, when measuring fluids like water, you want to check for the meniscus hitting the 200 milliliter line, which is the bottom of the curve. And lastly, for step 6, make sure that everything is combined, which means swirling the flask until everything pretty much looks mixed. And that's how to create a solution, and I don't think you have to actually use up all 6 blanks, but you pretty much just want to make sure that all your information is covered. Okay, and then next up for question 3D, we've got this equation, and now we have to draw what the reaction would look like at a particulate example. And we also want to make sure that they are in their correct phases. And so I've enlarged the picture here, and it's already given that there are 2 molecules of aluminum in there, which is a huge help, and I'll explain why later. Notice how the aluminum is touching together because it's solid. Okay, now that we have the equation and everything ready, it says that for every 1 mole of the solid aluminum, it needs to react with 3 moles of the silver ion. And if all of that goes well and all of that's consumed, then 1 mole of the aluminum ion and 3 moles of the silver solid will be produced. Now, using that information, let's go ahead and use the diagram to depict how that's going to be done. So for every 1 mole of the aluminum solid that is used, it's going to take 3 moles of the silver ion. So I'm just going to go ahead and cross off 3 moles of the silver ion. And so next up, that's going to yield 3 moles of the silver solid. And again, I'm putting the molecules kind of close together so it shows that it is in a solid form. And then it'll also yield 1 mole of the aluminum ion. And so since this is in the aqueous phase, I'm just going to place it randomly dispersed in the water. Don't keep it connected to anything. And it should look like that so far. Okay, so it looks like we have some more molecules in the first beaker, so let's go ahead and do the exact same process, which is super easy. I'm taking 1 mole of the aluminum solid and crossing that off, and I'm reacting it with 3 moles of the silver ion, so 3 is crossed off, and it will yield another 3 moles of the silver solid, and again, I'm placing that next to the other 3 solid silver molecules to show that it is indeed a solid, and then it will also produce the extra 1 mole of aluminum ion. And again, it is aqueous, so it'll just be randomly dispersed somewhere. Now, when I go into react it again, it looks like I have enough of the aluminum solid. You only need 1 of those. But I need 3 of these silver ions, and I only have 2 left. So those are not going to react, and it's going to be left in the first beaker. So in my second beaker, now that I have the extra 2 aluminum solid molecules that did not already react, I'll also be adding in the 2 extra silver ions in there because they did not react with anything so far. And again, I will keep it randomly dispersed because it is in the aqueous phase. And there you go. That's pretty much how the diagram should look like. And oh yeah, also funny story. While I was taking the test, I actually had no idea what they were asking on this question, and I was so confused. And I think you can use like an ice table or something. I don't really know. I heard someone use that. But I had no idea where to begin with this question. So, actually midway during this one, I had this like special epiphany about midway through, and I eventually figured it out using this method. I just crossed off a bunch of the ions in the first beaker, drew some in the second, and I eventually got the answer. So it's kind of a little story to like, just keep trying. Even if things don't seem to be right, I promise you, just go with your gut. And then for question 3e, we've actually got a reduction potential table, and it asks us to find the value of delta E. So I'm just going to bring back up the table for reference. And now this is a super quick shortcut that my teacher taught me, but you basically just want to flip the most negative E value, and then the second part of this is that you want to add that to the other E value that you did not use. So using these rules, I want to take the most negative E value, which is the negative 1.66 volts, and make it positive. So now it is actually positive 1.66 volts. And now I want to take that value and add it to the other E value, which we didn't use, which was the 0.80 volts. And so I'm just going to add these two together, and you get a value of positive 2.46 volts as a final answer. Pretty simple if you know what to do. And then for question 3F, we're asked about what delta G would be given delta E. Well, we knew from our last problem that delta E is positive, and I'm actually going to create like a little table here. So if delta E is positive, then we know a couple of things. First off, we know that it is spontaneous, meaning that it will naturally favor equilibrium without any energy input. It is also product favored, meaning that K is, of course, greater than 1. It is also known as a voltaic or galvanic cell. And lastly, that delta G is indeed negative. But how do we actually know that positive delta E corresponds with a negative delta G? Well, we can justify that using our answer using this equation. The lovely delta G equals negative NFE. Literally like the only equation I actually memorized because of how short it was. So looking at this equation, we know that the N is the number of moles, which is always positive. You can't have like a negative number of moles. That's like not a thing. And then now for F, that actually stands for Faraday's constant, which is 96,485 coulombs per mole of electron. Wow. Which that number, of course, is going to be positive. And for delta E, well, from our last part, we found out that it was positive. It was a positive 2.46, which is positive. So since everything is positive, that's good, but then there is that negative in front of the N. And so what this means is that the delta G will also be negative because of that negative. So to answer the question, we can put our claim that delta G must be negative because according to the equation, everything was positive, but there is a negative out in front, so the delta G will therefore become negative as well. So for this justification, just use the equation and kind of explain what was positive, what was negative, and how that will contribute to a negative delta G. And then for the last question, which is 3G, this one mentions that the reaction stops progressing, and what would happen to delta G? Well, to answer this question, we need to know what it means when the reaction stops progressing. Well, when the reaction stops, nothing is reacting and nothing is happening. So the E, or the cell potential, or the voltage, so if all of that is stopping, then delta E must be 0. And according to the equation we used in the last part, well, if delta E is 0, then anything multiplied by 0 in the equation should be 0. So delta G must also be 0. And that's your final answer. This also happens to be the last part to FRQ number 3. We finally got there. And as always, here are my score predictions. Of course, these are not the official AP College Board score predictions. These are simply my own and kind of what you need to get based on previous scores and also like previous bell curves and whatnot. And as always, thank you for watching. Make sure to subscribe for future videos. I'll actually be posting the next few FRQs. I think there's 4 of them left pretty soon. And just a reminder that I do have answers posted for the second FRQ, which is on the right, so just click on the video link. And I also have answers to the AP language test, so click on the video on the left. Hopefully this whole video link thing works because I'm very new to this. So yeah, and as always, have a fabulous day, and I guess I'll see you guys next time.